Welcome to our control seminar. Today, I'm very pleased to introduce Professor Nikolai Matni from University of Pennsylvania, who is going to give a talk on what makes learning to control easy or hard. And Professor Matni has been at UPenn for almost 6 years now.
Yep, start of the 6th year.
And he did his studies, bachelor's and master's at the University of British Columbia, and his PhD at Caltech. His work has been recognized already by a number of very prestigious awards, including NSF Career Award and a YIPA Award, Young Investigator Award from the FOSR, the George Axelby Award, the Google Research Scholar Award, and a number of Best Paper Awards, along with many other achievements and accomplishments. And with that, I would like to welcome him to our seminar series, and please join me in welcoming him. Thank you.
Thanks, Mika. Thanks everybody for coming. It's always nice to get an applause at the start. Like that takes the pressure off of getting one later. Very excited to be here. I appreciate everybody coming in on a Friday afternoon. I will do my best to be entertaining and lively, even though we're talking about math. What I want to talk to you about today is this question of what makes learning to control easy or hard. It's a question that we've been thinking about in my group for the past 4 or 5 years. I think, for this audience, we have folks coming from controls backgrounds, from robotics backgrounds, from various safety critical applications. I don't think I really need to motivate or convince anybody here of the importance of taking learning enabled components, which now these days are kind of inevitable, and integrating them into decision and control stacks in a way where we can say something meaningful about safety guarantees and things like that. We've all seen the videos of the robots falling over and the Uber car, the self-driving cars driving somewhere where they shouldn't. Things like that. So what I would like to do instead is, motivate this question and why we've been thinking about it from a slightly more pragmatic perspective that I think might resonate with the students in the audience, or at least folks who still actually have to worry about training neural networks, which is this idea of graduate student descent. Right? Yeah. So I think we've all been there, right? We have this great new exciting idea for a new learning enabled algorithm, a reinforcement learning problem. We go to implement it and then we test it out in MuJoCo, and it doesn't work the first time around. It starts to train and then our training curve diverges. Well, deep reinforcement learning in particular is very known to be finicky and sensitive to hyperparameters. So maybe after fiddling with this for a little bit, I start messing around with the learning rate. That does a little bit better, but it still blows up on me. Then I'll spend some time thinking about, changing my different activation layers and the different architecture and all of these things. And, next thing I know, it's been 2, 3 weeks, a month, 2 months that I've been staring at these training curves, and I start to have nightmares about them, right? It's just not working. And the question is, the fundamental question in this context is, why isn't it working? Why isn't my little MuJoCo man running in the way that I would like it to? Our take on this is that there are fundamentally 2 different situations that might be happening here, right? One is that I just haven't put in enough time and effort yet to figure out the right set of hyperparameters. And with a little bit more luck, a little bit more effort, a little bit more clever data collection, and maybe I'll be able to converge on a good controller. Or on the other hand, it could be that the problem that I'm trying to solve is just fundamentally hard, right? No matter what I do, even if I was able to get my hands on the best policy, I would still end up with these kind of bad-looking training curves. And I think the challenge, and really what motivated us to start thinking about this question of what makes learning to control easy or hard, is we really don't have a systematic way of disambiguating between these 2 situations. We don't know if we should be, just spending more time, investing more effort in hyperparameter tuning, or if there's just a fundamental limit that we're coming up against, right? So the motivation for today's talk is coming up with a formal, rigorous, systematic answer to this question, or at least making progress towards such a question, such an answer. And we're going to, there's comments online that the camera is adjusted, it needs to be adjusted because they can't see the slides. It's coming from me? No. And so maybe while we get that sorted out, the idea here is that, to answer this question, to come up with a systematic way, we're going to take inspiration from a different branch of applied math, which we all love and know, which is control theory, and in particular, robust control theory. I'm sure you've all taken either, Pete Seiler's class, and you've all learned about H-infinity and mu synthesis and all those kinds of things. We're not going to use those ideas, but rather we're going to use, what I think is a very underappreciated element of robust control, which is this idea of fundamental limits. Right? Fundamental limits say that there are some systems that cannot be controlled well. No matter what I do with them, no matter what policy I play, no matter what controller I deploy, it's going to lead to poor closed loop behavior. Right? And that's kind of what I mean by this idea of fundamental limits. And just to illustrate this, and I recognize that for this audience, this might be familiar, but it's always nice to start with a review of things that look familiar to us. I'm going to use this example from my PhD advisor that illustrates these ideas very nicely, which is this idea of trying to balance an inverted pendulum using my hand. Right? And so for this system, we can very clearly characterize the fundamental limits of a control that are achievable. On the one hand, there's a notion of the hardness of control that's imposed by the badness of my dynamics. So in this case, I can characterize the badness of my dynamics in terms of an unstable pole, which basically scales inversely with the length of this stick. So if you've ever tried this and you have an adjustable stick, the stick is really long, it's going to be very easy to balance. If I make it shorter, it falls over faster, right? And this is characterized in this context. In addition to bad dynamics, we also have this issue of potentially having to deal with bad sensing. In this case, I'm going to call this notion of fragility that, if rather than looking at the tip, if I have a long stick, but let's say put a baseball cap on and I look kind of halfway down, this actually leads to a much more difficult situation. What I'm doing is introducing an unstable zero that basically prevents me from detecting certain movements in this stick that I need to be able to stabilize things. Right? Bad dynamics on their own, not terrible. Bad sensing on their own, not terrible. But if you layer the two together, you end up with a lot of trouble where we can, using very rigorous methods that I know are familiar to a lot of you in the audience, we can characterize this amplification from sensor noise to error from vertical that scales roughly like 1 over where I'm looking on this stick. Right? You can imagine if I'm looking all the way at the bottom and only seeing this point here, I don't get to detect any movement at all, and it becomes impossible. And this is characterizing that. Right? And so, the main message here is that for these kinds of control problems, if I had bad dynamics and I layer on top of it bad sensing, I end up in a situation where it's just impossible to control them. In this case, it's through it's measured through the amplification of sensor to noise, sensor noise to error. And this is often where, if you're learning this in a first-year graduate level control class, things would stop. But I want to add just one last little element here, which is if I find myself in this situation, I'm looking at a problem, I run this analysis, and it says, uh-oh, I'm in trouble. It doesn't mean that I give up. It means that what I actually need to do is I need to change my system. Right? So in this kind of toy example where I'm putting a baseball cap on to mimic bad sensing, means I should look back up. Right? Okay, so this is roughly, the philosophical or spiritual inspiration that's going to be behind the rest of today's talk. And we're going to try to take these kinds of ideas and carry them over into this learning-enabled controlled world. So with that in mind, the question that we're going to be addressing today is what makes learning controllers from data generated by a dynamical system, like the one we saw on the previous slide, easy or hard? Right, this is really what we've been thinking about in my group for the past 5-6 years. And we've converged to an informal meta-theorem that goes like as follows, right? Which says that good optimal controllers that lead to a good closed loop. And now what good closed loop might mean something different in different situations, they're going to be easy to learn. I'm not going to have to be particularly clever in terms of how I design my learning algorithm. It won't be particularly sensitive to choices of hyperparameters. I'll just get to them easily. And conversely, if I'm in a situation where even the best optimal controller leads to poor performance, like the example that I had on the previous slide, then they're actually going to be very, very difficult to learn. I'm going to have to invest a lot of compute and a lot of time in collecting data to converge to this optimal controller that even once I find it, leads to really, really poor performance. Right? And so what I want to spend the rest of today doing is taking this informal meta-theorem and unpacking it and making it a little bit more rigorous. So with that in mind, here's the roadmap for what we're going to talk about next. We're going to start with the bad news, try to get that out of the way first. And we're going to talk about what makes learning controllers hard. And in this case, it turns out we don't have to go to any kind of any complicated system. Just looking at linear systems, we'll see that interesting classes of linear systems can actually get us into trouble. Right? And what I mean by all of that will become very clear in a little bit. And as we go through this discussion, we'll also get a very brief survey of positive results in this space as well. And we'll see kind of what they're hiding and what you have to worry about. Once we've gotten this bad news out of the way, we'll move on to thinking about the kinds of conditions we might ask for learning to become easy. I'm not going to consider the broad nonlinear control problem. We're going to use imitation learning as a very interesting, a nice case study that illustrates some of the concepts that I'm trying to convey. And then if we have some time, we'll also talk a little bit about what we can do if we're in one of these hard to control situations and I can't change my system. Maybe I can leverage big data from related tasks to make the learning task a little bit easier. Before I move on, I just want to say a couple things. First of all, feel free to interrupt me, ask me questions at any point. The talk is designed to be very modular, so if we get stuck on one of these, I can just skip the last part and it won't really affect anything. And if anybody wants to hang out a little bit longer, we can do that. Yeah, Gabor.
About the pendulum. So I qualitatively understand, this kind of issue where I'm looking at. But when we do these control designs, we typically just use the angle. So it's like somehow this distance is converted to the angle error. How is that?
Yeah, so if you could measure the angle, you're done. None of these hardness results matter, right? The hardness comes from the fact that I have bad sensing, right? Which is I'm only able to see the point of the stick and the unstable dynamics mixing together. So you're absolutely right. If I'm able to directly measure the angle, easy, right? It's this interplay of ill-conditioned sensing with bad dynamics, right? What's happening, from a quantitative perspective is my unstable zero is very, very close to my unstable pole. So I'm very, very close to losing observability of this unstable mode. Yeah, absolutely. Great. Okay, so that's actually a perfect segue into our next slide, which is the question of I showed you this example of a system that is hard to learn. That's hard to control. One question, and it's not obvious, is are these systems also hard to learn to control? It could be that sure, the optimal controller is not the best. It's pretty fragile. But maybe it's still easy to find using data-driven methods. And actually how we got started in this kind of line of research was using this system. We just thought, well, let's try to run some experiments and see what happens. And towards that end, what we did was we built a high bullet simulation of exactly this system. So what you have here is this little pendulum on a cart that slides in this one direction along this green rail. And this black bit at the top there is basically we're not allowing the controller to see that. Right? So this is our way of introducing this quantitative notion of control difficulty. The more I black out the stick, the harder it becomes to control in terms of, in light of that previous slide that I showed you. And we trained a whole bunch of different controllers using reinforcement learning here. We did 3 varieties, I think. We did one where you only get a noisy observation of that point, so no vision-based stuff. We did a pixel-based version. We also did a depth-based version. And surprisingly, all of them ended up having the same kinds of behavior. And I'm going to show you a representative training curve that came up in this context. So what I'm showing you here is the running reward of a soft actor critic, just kind of vanilla RL algorithm. Episodes on the right, on the x-axis, reward on the vertical axis. Up top at 500, this just means that I'm able to keep the stick upright within some region without it falling over. And what we're plotting here are the different training curves associated with different levels of control difficulty as measured by this fragility, the amount that I'm blacking out. Right, and what you see is this really striking matching between, if I'm reading this from left to right, it's going from easy to control to hard to control. And you see, as we make the problem quantitatively harder to control, we see that the training curves get worse and worse and worse until eventually it doesn't learn anything. Right? This isn't a proof of anything, but we saw this empirically, and this is really what motivated us to try to think about what kinds of problems could I study to maybe understand underneath the hood what's happening and what leads to this. Okay, and so that's what we're going to do next. So we're going to introduce a stylized version. It doesn't capture all of the complexity of this problem, where these kinds of hardness, quantitative hardness results can be shown. Okay, good. Yeah, so the main takeaway here is that bad optimal controllers are indeed hard to learn, at least from this empirical demonstration. So we're gonna ground things in the problem of learning to control linear systems. And I want to make sure that we're all on the same page here. So we're going to be considering system dynamics that are linear time invariant. So again, I know everybody knows this, but my state here is going to be the x of t. My control input is going to be ut, and wt here will be my disturbance process. And in terms of modeling what's known and not known about this system, I'm going to assume that I have known functions a and b that map some unknown parameter to the state space matrices. Right, so this allows me to capture either fully unknown dynamics, in which case, A and B just become entirely, subsets of this parameter theta. But suppose I have some physical knowledge of my system and I just want to embed parametric uncertainty that I want to learn. This allows us to capture that as well. And then, we'll keep the noise standard, just IID, white and time Gaussian. You can generalize this a little bit, but it's not really important to the story here. We're going to be using, linear systems, and we're going to be using LQR optimal control as our baseline here. Again, as a reminder, what LQR optimal control seeks to do is minimize the steady state variance of this weighted sum of my state and actuation error, basically measuring the amplification from my disturbance process to these two terms. Why do we like LQR? Well, from a control theoretic perspective, we know everything there is to know about it. I can give you a closed form expression for the optimal cost as well as the feedback gain. We know the optimal feedback policy is a static state feedback policy defined in terms of a time invariant matrix acting on my states. We solve a discrete algebraic Riccati equation to get all of these things. Right? So, why is this the problem that we decided to study? Well, linear systems and LQR, they're useful benchmarks, right? On the one hand, they are not fully general. I'm not claiming that these capture all of the intricacies of, full-blown nonlinear data-driven control, reinforcement learning, things that you care about in a robotics lab. But they're still interesting enough to capture some very surprisingly rich behaviors. And you combine this with the idea that they're actually analytically tractable, they serve as a good testbed. Right? And of course, if I can show hardness results for this simple class of systems, this implies that things can only either stay the same or get worse for these more richer classes of systems. Okay. So let me introduce the learning problem that we're going to study, which is what we call learning LQR from offline data. This is a two-phase setup. There's an offline phase where we run experiments. And during this phase, I'm allowed to do anything to my system, and I'm not penalized for it, right? That's why this is called offline learning, right? As opposed to something that's online and adaptive. Right, so in this context, remember, as a reminder, this is my unknown system. I'm trying to probe the system to get information about these unknown parameters, theta in red. I'm allowed to play an exploration policy. I'm going to use blue to denote data generated by this exploration policy. And I just want to emphasize that it's allowed to be adaptive. So that's why we have that it's a function of the history of states that I've seen. Right, so this isn't constrained to just be like injecting white noise. I can do whatever I want with it, subject to some exploration budget. Right, so this budget here is just saying that on average, every time step, I get to inject sigma u squared energy into my system. Right? I have to limit this exploration budget as otherwise, for a linear system, identification becomes somewhat trivial. Okay. So that's the offline phase. Again, I can pick these in any way that I want, subject to this budget constraint. This will produce a data set of states and inputs. And then using this data set, my goal is to then synthesize a controller, which I'll call k hat, a function of this data set. And I'm just going to play this policy. Right? We know that the optimal policy has this form, so we're not losing a whole lot by restricting our search to this kind of class of systems. Okay. So this is the problem that we're going to talk about for the next 15, 20 minutes. Any questions about what we're doing here, or is this okay? Okay, good. So if we're still on board, what I would like to start with is just a very quick overview of positive results, telling us when we can do this efficiently. This is, for those of you who have interacted with the Learning for Dynamics and Control community or conference, right? This is the kind of problem that we've been studying for the last 5, 6, 7, 8 years. And we have a very good understanding as to when we can, what we can do and what we can't do. So the first thing that I need to tell you about is how we're going to judge the quality of this approximate learned policy. And we're going to measure this in terms of suboptimality with respect to the optimal cost. And so this term of excess cost, which I'll use repeatedly throughout the next few slides, is how we're going to measure things, right? And what we're doing here is we're looking at the cost achieved by my approximate policy synthesized using this collected blue data set D versus the optimal cost had I known the true system. And here's a flavor of what a positive result looks like. What this says is that with high probability, if I collect enough data, where enough data is something that scales very benignly with both the accuracy that I'm looking for and the underlying state dimension of my system, then I'm going to get a controller that comes with an epsilon of optimality. Right? So, for those of you who have a little bit of a learning theory background, what this is saying is essentially this offline LQR problem is pack learning. And just to give you an example of a typical algorithm, a typical implementation that achieves this, Suppose that I had a fully unknown system, so I need to learn A and B from scratch. This typically an algorithm that achieves this kind of statistical rate says during the experiment phase, don't have to be clever. I'm just going to inject white noise that satisfies my input constraints. Collect this data, and I'm going to turn my synthesis task into a two-step process, one where I do system identification. Since I get to measure the full state, sysid here is just a least squares problem. This is going to output some estimates A hat and B hat. You can show that if I have enough data, these estimates are an accurate enough representation of reality that I don't have to do anything clever during control synthesis. I can do what's called certainty equivalent control and just pretend that A hat and B hat are the true system and output that controller. Yeah.
Is there a difference between learning A and B or learning the poles and zeros?
Yes. Okay, I want to be careful in terms of how I answer this. From a controls perspective, not really. From a algorithmic perspective, we understand how to solve this problem and analyze it a lot better. For a system like this, there actually the only thing that you're worried about here are poles, unless there are delays that are baked into here in terms of the control input, because it's a full state, a fully observed state system. Yeah. So I want to mention also that this is an upper bound, right? And so when I talk about the lower bounds later, it will be for any learning approach. To show an upper bound, I just need to give you an example of an algorithm that achieves this rate, right? And this is a very simple algorithm. It's very familiar. It's what anybody would do as a first guess. And I think the surprising thing for us in this kind of learning for control space was, in a very precise sense, this is actually statistically optimal. Okay.
Nikolai, just
yeah.
Do you need an underlying assumption that A is stable, or it doesn't need to be stable?
No, it doesn't need to be stable. So when we first started, we needed A to be stable to be able to analyze the error here. There's been, again, I don't want to get into the details too much, but as long as A doesn't fall within a certain pathological subset of systems where I have very unstable modes and very stable modes, this works. Yeah, absolutely. Okay, good. So, that was just meant to be a flavor of what a generic positive result looks like. And so this part of the talk is supposed to be about hardness results, right? And I've just basically showed you that this isn't hard. This is easy. So what's going on, right? You'll notice that I've been conspicuously quiet about this constant in front here, which is, in the literature, it's called a system theoretic constant that depends only on the underlying parameters of my true system. And the implicit assumption in all of this literature is that this term here is well-behaved. And by well-behaved here, it either actually scales like a constant relative to the full system, or at least it scales polynomially. So what I'm going to show you next is that there are, in fact, very interesting classes of systems. These aren't pathological. They're not particularly unrealistic, for which this constant here can actually be very, very big and exponentially large in the state dimension. Right? And this is actually going to show you that there's a hardness result underlying this a certain class of systems. But before I do that, what I need to tell you about is how are we going to talk about lower bounds from a learning theoretic perspective, and how are we going to relate that to system theoretic properties? So here's our starting point. For a particular system, for a particular instance theta in red here, our particular unknown system, we're going to ask what is the best possible performance by any algorithm, right? So that two-step process that I showed you previously, both how I design my exploration policy and both that synthesis algorithm, they can be anything. We're not restricting ourselves to anything that's computationally tractable or anything like that. I can have infinite compute. I'm allowed to do whatever I want, right? So these are what are called information theoretic lower bounds. So you might imagine, one way of kind of setting this problem up would be to pose it as kind of a pseudo optimization problem where I'm going to infamize over all possible choices of these exploration and synthesis algorithms, right? And try to minimize my excess cost. And I'm using this alg here as a little placeholder to indicate that. Now, this is what you would like to do, but unfortunately, you can't use this directly. Because I'm allowing myself to infamize over any possible algorithm, and I'm not putting any restrictions on it, my algorithm can just cheat and spit out k star of theta. Right? So this is, I'm just going through this because this is, I'm going to introduce a way of circumventing this problem that looks maybe a little bit different than what you might expect. And this is why we're not using this very natural thing. Again, this is something that's well recognized in information theory and what are called minimax lower bounds. And so that's what we're going to do. We're going to take this original problem and we're just going to relax it or dilate it a little bit. And we're going to say, not only should my algorithm work for the particular instance that I care about, but it should also work well on nearby instances, right? So this prevents this algorithm from cheating, right? By restricting it to having to work well on a ball of systems around the thing that I care about. But also by tuning this radius that I look at, I can still get, what are called local or instance-wise bounds, right? So the bounds that I'm getting are relevant to the particular problem that I care about rather than kind of this global minimax, which is very easy to kind of break and lead to hardness results. Yeah, sorry.
Do you have any restriction on how you like the data?
So the only restriction is an energy budget.
So you can reset the system whenever.
Yeah. This is, you have, you can do whatever you want. Yeah. Good. Okay. And so let me give you an informal main result, and then we're going to unpack it a little bit. So here's my informal main result, which is, if I have enough data so that, some nice things happen on the mathematical side of things, I can lower bound this minimax excess cost in terms of a very interpretable quantity that scales with up top how hard it is to control my system, and down below the amount of data that I collected, T. And so sorry, so this result is for a single trudge experiment. There are versions of this that would work for multi-trudge. Yeah. And also the difficulty of identifying, or the easiness of identifying my my system, right? So what I'm going to do on the next slide is unpack this and actually show you a little bit of math that goes behind this, especially for the control theory experts in the audience. Hopefully, just give you a flavor of what these things are actually encoding. So this is the exact same bound that I had on the previous slide, and don't worry, things are color coded here, so we can kind of unpack these different quantities and understand what they're doing. So the first quantity that I want to highlight is on the right here in green. And this is the derivative of my optimal controller with respect to the underlying parameter theta, right? So this tells me how much my optimal controller changes if I jiggle my system a little bit. Another way of saying that, of thinking about this, is this quantifies the sensitivity of my optimal controller to errors in my learned theta, right? For those of you who worked with information theory a little bit, you might recognize a Fisher information kind of Kramer-Rao lower bound sneaking underneath the hood here, right? Good. That term, this kind of sensitivity to learning errors, is multiplied by this term that is mapping errors in my control effort or my control action to my control cost. And what I have on the end there, this sigma x, is a controllability gradient that captures how much noise process is amplified in my cost function, right? So what the numerator is telling me is how much errors, how sensitivity in my controller is amplified and reflected in my optimal, in the suboptimality of my cost, right? The denominator, I'm not going to unpack it too much. This ends up being kind of a product of controllability gradients as well. And this basically quantifies how easy it is or how difficult it is to excite my system with my exploration policy. So how easy it is for me to get information about the underlying system, right? So the reason I'm showing you this is that it very much suggests a strategy for constructing hard to learn to control instances. If I can build a system where either the numerator is very, very large or the denominator is very, very small, then I can show that this minimax excess cost is actually quite large, right? And I can get myself into trouble. So what I would like to do on the next slide is give you an example of such a system where these bounds end up being very bad. Right? And so the main punchline here is that what I'm going to call a high gain chain is hard to learn to control. Right? So here's the learning problem setup. Here are my dynamics. I have an A matrix that's this kind of upper triangular banded system that's encoding basically a chain, and a control input comes in at the bottom. Right, and the reason I'm calling this a high gain chain is if I apply a control action, let's make that be that little blue square down here. What the system does is it propagates this little blue block up the chain, and every time it goes up, it doubles in size. Right? So by the time you get to the top, it's quite big, right? So that's what I mean by it's both high gain and underactuated. The particular numbers here are not super important. We kind of pick these just because it's a stable system, right? It's triangular. All the eigenvalues are 0.9, and you can replace the 2 with like a 1.01, and the same idea would go through. Just the constants wouldn't be as nice. Okay, just wanted to emphasize that. In addition to all of that, in terms of the learning problem, I'm going to assume that I know the A matrix, and the only thing I need to learn is the B matrix, right? Which is kind of surprising. This was actually inspired by some beautiful work that Nechmia did. Also, in terms of kind of characterizing these kinds of fundamental limits of control, where even if you know everything except for parts of the B matrix, you can still get yourself into a lot of trouble. And then just to make sure, so you know that I'm not hiding anything, my cost functions and my noise process, it's all just one, right? So we're not doing anything crazy there. So what the result we're able to show is that my minimax excess cost here is in fact lower bounded by something that is exponential in the state dimension. Right? This kind of interplay again of underactuation, right, and bad dynamics is what gets me into trouble. Right? So looking at this, anybody who has a control theory background knows that the optimal controller is not going to give me great performance because of this structure. What we showed is that this bad optimal performance translates into very hard to learn to control systems as well. And the idea here is that this control hardness term is one where small errors in my learned policy are amplified exponentially. So just to go back to our little cartoon here, if this red square is the error that I'm introducing now, then as it propagates up the chain, it blows up on me. Right? And again, I know that for a control theory audience, you don't necessarily need this animation, but I also give this talk to computer scientists, so it helps to have pictures. Sorry, Bernadette. Okay, great. So, what I want to mention is, I've given you a specific instance of a hardness result for this offline LQR problem. And this is, one result in a family of results that we've been thinking about. So a lot of folks are interested in this idea of online or adaptive LQR, in which case you measure the performance in terms of regret, where you're comparing the performance of your adaptive controller to the best possible controller in hindsight. And we show that a similar, it shows that a similar kind of system can get you into trouble, but there the intuition in terms of what's going wrong is in adaptive control, I have to balance between probing my system and controlling it, and these kinds of high gain chains end up being hypersensitive to exploration. Right? This exploration is a suboptimal action. If that gets blown up on you exponentially, like on the previous slide, then you can get into trouble. Now, you might also be thinking, okay, well, maybe I'm asking too much of my learning algorithm to find an optimal controller. What if I just care about stabilizing my system? Turns out that even offline stabilization can get you into trouble as well. In this case, the control hardness problem goes away, and it really kind of reduces down to a system identification bottleneck. And we show that in this case, interestingly, if rather than having a high gain chain, you have a chain that damps the excitation that you put into your system, then this can actually get you into trouble if what you need to learn to stabilize your system is at the end of this chain. And so, I'm not expecting the details of all of this to have been, come across, but I just want to let you know that we do have, a full family of results characterizing these ideas in pretty much any kind of optimal or stabilization problem that you care about. And the main takeaway, the main story here is that either if I have an underactuated system that's either too excitable, this idea of high gain chains, or not excitable enough, depending on the problem that I care about, this could get me into a situation where I need exponential amounts of data, exponentially large amounts of data to learn the system, the policy. I think, for people with a robust control background, this is, even though these look like negative results, these are very, it's almost comforting to see this, right? It tells us that, our familiar notions of ill-posedness and ill conditioning from robust control translate to learning theoretic hardness as well. So, next time your RL friends are telling you that, oh, we can just throw RL at it, not so fast, right? Good. Okay, so, if we come back to our meta-theorem, this is, half of our meta-theorem, what makes learning to control easy or hard. Before moving on to the second part of the talk about the good news, I just want to circle back to this idea of, okay, my controller is hard to learn, now what? Like, what should I do? Should I just, throw up my hands and give up? So it turns out that we actually have matching upper bounds to these lower bounds as well, which says that our excess cost is also upper bounded by terms that look like this, right? So this also tells us that if I have control over the design of my system, if I can alter the hardware, if I can alter the physics, if I can alter the sensing and actuation, then I can push these results down, right? So for example, if my control hardness term is too high, right? This is typically because my system is too excitable. Well, what should I do in that case? Well, maybe I can modify the physics and add damping, right? And this is I've been talking to some folks at Penn who work on soft robotics, and this is something that, is very much physically realizable. Conversely, right, if my system is not excitable enough, if my sysid term is what's killing me, then maybe this suggests that I need to add more actuators. Again, something very physically realizable in, say, the context of soft robotics. The reason I'm bringing soft robotics is they're continuum dynamics. If you discretize them, they look very much like these chains that I described. Okay. Good, so, this this gives us the potential of starting to reason about a really interesting co-design task, right? Which is, if I'm in this data-driven control setting, and I'm only given structural knowledge of my system, right? I know that it has maybe this chain structure or something like that. I know that it arises from discretizing a continuum model. What should I do to change the physics to make it easy to learn to control? I don't have any answers. I don't have any quantitative answers, but I think this offers, a framework for reasoning about this in a nice way. Okay, good. So we've gotten the hard part, the bad news, out of the way. What we're going to do next is kind of switch over and look at some maybe positive results. Again, let me just take a second here and see if there are any questions about what we just went over. Okay, good. You're either all following or I've lost you all, but we're going to keep going. So, for this part of this next part of the talk, I'm trying to understand. Yeah, Pete.
Yeah. When you started, I guess I was thinking like the traditional robust control fundamental limits are things like time delays, right half plane zeros, right half plane poles, and this has kind of nothing to do with those type of fundamental limits. I guess when I have a question, it's just more a comment.
Yeah, I mean, so here's my take on how this connects to the kind of the traditional robust control stuff, right? Which is this shows you that as in the classical ideas, what matters are the singular values, right? And so what we're basically showing here is that the closed loop singular values are what control the hardness to learn. Right? The way these things look like is you end up with a lower bound of something that looks like your closed loop Riccati equation or something like that, and that captures whether I'm able to attenuate things or not. And so it is connected. It's not quite as it's a simplified problem, right? So we don't have this interaction between like unstable zeros and unstable poles. It turns out that was really surprising to me, which is you didn't need that complexity to still get yourself into trouble. I suspect that if you add in that extra complexity, it'll get even worse. Still working on figuring out even more bad news, but not there yet. Yeah. Thanks, Kevlar.
Question. So that simple example with the A and the B matrix. So you give us the A and the B, but your C matrix is full ones, or what do you expect? Because I guess that...
So this, in this very simplified setting, we're assuming we get to measure the full state. Yeah.
I see.
And that comes back to like Pete's question here, which is this should be easy, right? Like at least what we learned in control is this should be easy, but it turns out that this underlying notion of ill-conditioned control problems where, yes, I can compute an optimal controller, but it's going to have a really bad optimal cost. That actually reflects in the learning complexity as well. Yeah. Great. All right. Awesome. Thanks for the great questions. Yes.
Quick question. Is bad optimal cost somehow correlates with the set of, like the size of set of stabilizing controllers?
That's a great question. I don't know that I have any insight on that. In the context of when I'm saying bad optimal cost here, I mean a closed loop LQR optimal cost that is exponentially large in the state dimension. Right. That's so maybe there's a connection to the volume of stabilizing controllers, but we haven't looked into that. I think that's a great question. Oh. Okay. I think oh, no, we can. All right. So let's keep going. And we're going to talk about positive results now in the more general nonlinear setting. We saw a flavor of what positive results look like in the linear setting. To ground our discussion a little bit, I'm going to use imitation learning as a case study. And so the first thing I'd like to do is just make sure that we're all on the same page in terms of what I mean by imitation learning. So here's the typical setup when people talk about imitation learning. I'm given some expert policy that I like that's maybe not scalable enough for the application that I have in mind. So this expert policy could be a human. It could be a computationally heavy, let's say, nonlinear MPC or ILQR algorithm, or it could be a very large neural network that is too big to put on the hardware that I care about. And the way that, the goal is to take this expert and distill it into something that I can use in the context that I care about. And an approach for doing this is to collect a data set of labeled pairs of state action xt and the corresponding expert action pi star of xt. I'm going to use blue throughout this part of the talk to note expert data, and to solve a supervised learning problem where I'm trying to learn an approximate policy pi hat. We're going to use red for my approximate policy that mimics my expert policy as close as possible, right? Or that imitates it. That's where the name imitation learning comes from. In the most kind of basic version of imitation learning, I then take this outputted policy, which is going to be a function of my expert data, deploy it on my robot, cross my fingers and hope for the best. More sophisticated versions will take this new test data, fold it back into my expert data, and kind of rinse and repeat. And I'll talk a little bit more about these more sophisticated versions in a little bit. What I'd like to do here is kind of highlight what are the potential pitfalls or challenges associated with imitation learning. So first of all, people like to use imitation learning if they can get away with it rather than reinforcement learning. It tends to be much more sample efficient. There's a lot less things that I have to tune. And at least my brief stint working with folks in industry, imitation learning was always the first thing that they tried, and it was mostly the only thing they got to work reliably. The challenge, though, is that it doesn't always work, right? When it works great and it's fantastic. And when it doesn't work, kind of shrug and don't really understand what's going on, right? And so why does imitation learning go wrong? Well, here's the idea, right? I'm solving the supervised learning problem. And if I apply standard learning theoretic techniques, what allows me to give you are guarantees that say that my expert policy, my approximate policy pi hat, will match my expert's actions if I give it a new trajectory of expert data, right? Because that's the data that I've been trained on, right? Of course, this is not what I care about. I'm not planning on deploying my expert policy and then having my red guy just tell me what's happening or isn't. What I really care about is guarantees that my learned policy matches my expert policy on the data generated by my learned policy. Right? This is kind of gets you into a little bit of trouble because I don't have access to this distribution of data during training. So, what do I do? What can I get? What can happen? Right? And the issue here is that small errors can compound and actually kick you out very far away from data that you've seen during training. And I want to kind of illustrate this with a cartoon to give you a sense of what's happening here. So, the dangers of, what are called covariate shifts induced by these errors in the learned policy. So let's suppose that these trajectories here are my expert trajectories, and I'm going to use this cloud as a kind of cartoon version of my expert or my training distribution. Right? Suppose I run my imitation learning algorithm, and now I want to try a new test point and test initial condition at this black dot. Well, my expert policy would take a step in this blue arrow's direction, whereas my learned policy will do a decent job, but it'll maybe make a small error, right? Because I'm learning from data. So I end up over here. Expert still knows what to do. And even though I made a small error, I'm still within my training distribution. My policy has seen this kind of data beforehand. It still sort of knows what to do, so it makes a small error. Now the issue is this compounding additive effect of two small errors has kicked me outside of my training distribution. So whereas my expert might know what to do, my learned policy hasn't seen this data before, right? So it's going to do something even worse, which kicks me out even further, which leads to even bigger errors and ultimately failure. Right? This is a very well-recognized problem within the imitation learning community. This is really at the crux of why imitation learning is challenging. Right? So I'm not claiming that I'm the first person to identify this or anything. What we're going to try to bring as a new perspective on this problem is trying to understand how the expert affects sample complexity. What is a system sensitivity to imitation error? How does underlying robustness properties manifest in this scenario? So to kind of motivate our take on this problem and where we're coming from, I want to give you a very high-level overview of how people have addressed this problem. So what I just described is what's typically called vanilla behavior cloning, and what I've shown is that it's sensitive to this idea of covariate shift. There are two classes of algorithms that people have used to address this problem. One are a class of on-policy algorithms, so a representative being Dagger. And the basic idea there is I let my learned policy roll out a little bit, and then I'm going to let my expert come in and correct. Right? Kind of kick me back into my training distribution. Then I'll take this new data that I've collected, fold it back into my training, retrain, and kind of rinse and repeat. And if you do this in the right way, you can show that good things happen. There's also an off-policy approach. A representative example would be something like Dart from folks at Berkeley. And the idea there is while I'm collecting my training data, let's just inject some noise to preemptively puff out my training distribution. I know my learned policy is going to make mistakes, so why don't I just introduce mistakes during training so that my learned policy, so that information is available to my policy when I'm training. Outside of the low-level details, there's a key idea that's happening in both of these kind of philosophies, which is you're trying to show your learned policy how to recover from errors, right? Either through explicit corrections from the expert policy, or by kicking the expert off track a little bit and allowing it to keep going. Of course, there's an implicit assumption here, right? Which is that if I put my expert in a bad situation, it can actually do something reasonable, right? I'm assuming that my expert can recover from these errors, either introduced by the noise or by the errors in my learned policy. I mean, what's another name for something that can recover from errors? It's a robustness, right? So our take here is going to be, can I make explicit this assumption of a robustness in my underlying expert and quantify its effects on the difficulty or the easiness of doing imitation learning? So that's going to be kind of our agenda for the next 5 minutes or so. So why is robustability important? Let me actually introduce some math now to concretize our problem. We're going to consider a generic nonlinear control problem. So F can be any nonlinearity. We have underlying smoothness assumptions here. Typically, if anybody's talking to you about sample complexity, they're hiding a Lipschitz assumption somewhere. So we're talking about Lipschitz F. And the only randomness that we're going to consider is going to be in our initial condition. Right, so the idea here, the thing that I want to generalize across are random draws of initial condition. Once I draw my initial condition, the system is completely deterministic. And I'm going to, just to remind you of our color coding, I'm going to use blue for my expert policy and the data that it generates. And I'm going to use red for my test policy, my learn policy, and the data that it generates. Right, the crux here is going from blue data to red data. And so that's why we're introducing this idea. And we're going to measure the quality of our learn policy in terms of this imitation gap, which just looks at the difference between my test trajectory in red and my expert trajectory in blue over a horizon. And our starting point is a very trivial, but ends up being a very fruitful observation, which is I can take my test policy and write it as a perturbed expert. Right, this is the tried and true trick of adding 0 strategically to a problem. So I have my test policy in red. I'm going to rewrite it as my expert policy plus a perturbation. Right, where this perturbation captures the policy mismatch on my test trajectories. Now, I want to emphasize that all of the X's, all of the states are in red here. These are the states that are generated by my test policy being rolled out. Okay? So we're not cheating. And so if I introduce this notation, then I can rewrite my gap as a difference between a nominal trajectory of my expert and a perturbed expert trajectory. So at this point, I haven't done anything except introduce a bunch of colors and notation. But the idea here is this problem, the problem of bounding the gap between a nominal trajectory and a perturbed trajectory, is something that has been studied extensively in the nonlinear robust control literature. Right? And that's what we're going to tap into now. And it's going to be using this idea of incremental input to state stability, which I know a lot of you in the audience have worked with before. Again, just to kind of remind ourselves of our notation, my test policy pi hat generates the red states, and we're viewing it as a perturbation of my expert behavior, which is in blue. And we're going to assume that my expert policy satisfies this notion of incremental input to state stability. I'm going to call it delta ISS from now because I can't keep saying that mouthful. Which is basically saying that for any t greater than or equal to 0, I can bound the difference between my expert and perturbed behavior in terms of a forgetting factor and a robustness factor. Apologies to the nonlinear control experts in the room. Class KL infinity, class K, right? Okay, good. Right, so the forgetting factor, what this is telling me is it's quantifying the rate at which my system forgets differences in initial conditions. It's a notion of stability in trajectory space. Whereas my robustness factor is basically telling me how much perturbations are amplified in the difference between these different trajectories. Now, in this case, we're going to be assuming that we're going to be comparing expert and learned policy starting from the same initial condition. So the only thing that I need is this robustness notion, right? And in fact, we only need this to hold locally around expert trajectories. We don't need it to hold globally. So this is actually a fairly mild assumption, depending on how you pick your robustness function, right? I could be very, very robust, or I could be not robust at all. But typically, you'll be able to pick some function for which this is true. Right? And so if I have an expert policy that satisfies this condition, then I can upper bound my imitation gap in terms of this robustness function acting on my policy mismatch. Right? So let me just copy this over to the next slide, and let's talk about how we're going to deal with this. Right, so here is my imitation gap, and what we've shown is that we can bound this by some function that captures the robustness of my expert to these little perturbations, these little errors. But it's acting on this policy mismatch under my test policy pi. Right, so I haven't really done anything yet because I have no guarantees that this term isn't blowing up on me. Right, this cascading failures that I showed you earlier can make this thing in the argument here get very, very big. So we need to deal with that. So our first key insight was we're calling this adversarial criterion for generalization, which says that rather than asking for my expert and learned policies to approximately match each other only on the expert data, I have to expand this a little bit and ask for them to approximately match each other and sit on a tube around my expert data. Okay? And if this matching, this approximation on this tube is matched to the expert robustness, then I can guarantee that nothing is going to blow up on me. Right? This is basically saying that if I wander away a little bit, an epsilon away from where I should be, the expert is able to attenuate me back in. Right? So like maybe it bounces around, but I never escape this tube of radius epsilon. Right? And so we're able to guarantee this small imitation gap. So a couple of things, right? First of all, if you were happy just using this directly as an objective function in your imitation learning algorithm, then you could do this. But it demands kind of a lot, right? You're asking yourself to be able to query your expert policy at these random points within this tube. Not all experts can do that. If anybody here has ever tried to train a GAN or something like that, doing deep learning on any min-max anything is a nightmare, right? So theoretically, this works great, but we also wanted to give you a practical algorithm. And our idea was to use the Taylor series expansion of our imitation gap to deal with this. So the intuitive idea is I'm going to take this policy mismatch on my under my test policy pi, and I'm going to do a Taylor series expansion around the blue data, the data generated by my expert policy. Right? So why is this helpful? Well, the positive thing is that these terms in blue here are things that are defined in terms of data that I have during training. Right? So I can collect more of these guys, use standard machine learning, like stat learning theory, to quantify how these things go down with more data in terms of their error. The bad news, of course, is that I end up with this implicit gap, this implicit inequality, right? I'm trying to bound my gap, it's on the left, but it shows up on the right as well. Robust control people in the audience, small gain theorem, right? Roughly is what's happening here. Right, so if you squinted this a little bit, you should be able to convince yourself that if I make this term small enough, I can invert this and get a non-trivial bound. And that's exactly the insight that we had, but slightly more generalized. And this is this idea of Taylor series imitation learning that we introduced that says to ensure a small imitation gap, not only should I have pi hat match pi star, should my policy match my expert, I also want higher order derivatives to match. Right, you can think of these higher order derivatives as telling my learned policy how to make local corrections in the same way my expert policy does. And what we can show is that how high up you need to go in this Taylor series expansion depends on how robust my expert is. So for example, if I have a super robust expert that attenuates perturbations quadratically, right? So I have a small error, it becomes quadratically small, behavior cloning works out of the box, nothing to worry about. That being said, quadratic robustness is something I couldn't even tell you a physical system that satisfies that, right? More realistic would be something with linear robustness. And so if you have something that's let's say locally exponentially stable, a contracting system, if you know what that is, they all satisfy this linear property. Then what we show is if you match both the policy and the Jacobians, good things happen, right? We don't have this cascading failure. And in general, we can quantify this in a theorem that says for a new draw of an initial condition with probability 1 minus delta, I will have small imitation gap if I collect enough number of demonstrations. And at least for me, what was exciting here was the enough number of demonstrations scales with the hardness or the easiness of the control problem, of how robust my expert is. So, algorithm notwithstanding, what this shows is that if I have a very, very robust expert, both the learning algorithm in terms of the cost functions I need to include and the amount of data is less, and it degrades gracefully as my system becomes less and less robust. And so there's a very clear mapping between the robustness and the hardness of learning. And just a small example of these ideas at play. We took these different MuJoCo environments and we informally ranked them from more robust to less robust. On the left we have swimmer. For those of you who don't know what that is, it's basically a worm on the ground in viscous fluid. Right? So I don't think you can come up with a more robust scenario than that. And on the right, we have things that are a little bit more challenging, things like half cheetah or humanoid. And what I'm showing you here are behavior cloning, DART, the off-policy approach where you inject noise, and Dagger, the on-policy approach where you allow the expert to come in and correct things. And I'm comparing the vanilla version of these algorithms where I'm just doing policy matching, and what happens when I augment the terms with the Jacobian term as well. And what you can see, and this is kind of predicted by the theory, the very robust case, behavior cloning is great, right? I don't have to do anything sophisticated. But as I move out to these more complicated and presumably less robust experts, there's a significant gap. Introducing this additional information of Jacobian matching leads to a very large improvement in terms of my behavior. Right? Now, you may be wondering, how do I get access to the Jacobian of the expert policy? Fair question. You certainly aren't going to be able to do this for a human expert, but I have something like nonlinear MPC or ILQR. These are things we can actually query. Yeah.
Do you expect the data and that to be more robust than behavioral cloning, especially for the humanoid case? That's where we see like big difference.
Yeah, so you're asking why is this curve so crappy?
Yeah.
Yeah. So
Thought as well.
yeah. So for both of these, the learn policy just seemed to kind of get stuck in a bad local minima. No matter what we tried, we couldn't get it out of there. So we still see a little bit of an improvement, but both Dart and Dagger are they're kind of these iterative algorithms. And if your first learn policy is not very good, then you get into trouble. And in the data regime that we were in, it wasn't enough for these to kind of get out of those valleys. Yeah. Yeah.
There are possibility that your Euro controller is much more simpler than your expert, so that it cannot learn what is like in any cases. Right.
So the question here is like, what happens if the policy class that I'm trying to imitate an expert with can't actually realize the expert? Right? So there is an assumption in the theory here of realizability, which is whatever my expert policy is doing, there exists a policy in my policy class that can match it exactly. You can relax that a little bit, but at least for the theory to go through, we have this idea of realizability that does show up. In practice, none of these actually satisfy those assumptions, and it works fine. So yeah, but I think there's an interesting question there about distilling large neural networks into smaller neural networks, and what are the trade-offs there? Okay, yeah.
Start wrapping up.
Yep, I was gonna. So we're not gonna get to the big data part, but that's okay. Just kind of want to summarize here this idea of an informal meta-theorem, right? Where basically what we've shown is that controllers that are incrementally robustly stable are easy to learn. For the roboticists in the room, we also took these ideas and applied them to kind of this kinesthetic teaching setting where we actually forced ourselves to learn a model that satisfied these different kinds of incremental input to state stability properties by augmenting our learned model with a control theoretic informed term. In the interest of time, I'm going to skip the details, but the idea is we're eliminating spurious minima away from our data, and by enforcing this incremental input to state stability. Now, I'm going to just wrap up here, but I will just comment that we have another line of work that leverages this idea of big data and multitask learning, where I can use data from related tasks to learn a shared representation to make learning more efficient on a task that I care about. If anybody's interested, please, I'll be hanging around for a little bit after the talk. Happy to talk about that a little bit more. But I'm going to just wrap up here by summarizing our informal meta-theorem in terms of two pieces, right? Hard problems happen when I have an underactuated system that's ill-conditioned in one direction or another. And a notion of robustness in trajectory space is something that is very useful for learning over dynamic data. And it makes a lot of sense because that's essentially our unit of learning, our trajectories. And you can pull data from diverse tasks. And I cannot end a talk without thanking my amazing collaborators from both past and present students at Penn and folks and colleagues as well. And so here's a list of references of things that we talked about today. Thanks again for your attention and for the great questions on this Friday afternoon. Thanks everyone.
Maybe we can take one question. There is still one. Any questions? Please.
So just higher level, should I say? So I think you convinced us that these things are important, but I still wonder how can I convince my RL friends to say that doesn't work. In the sense that often what we hear is that this is true for like linear systems and you can prove all these things, but we have these really complicated nonlinear some things, right? And then probably this is not true there, right? So I just wonder what's your insight or what would be a good way to.
Yeah, so there are a couple of things there, right? Which is, I think, wait, is this recorded? So I think especially in the the early days of RL, a lot of the problems that people were considering, even very impressive looking demonstrations, the systems were extremely over-engineered. Like they were built to specifically eliminate all of these hardness issues that I've talked about. I mean, that the one that I think about the most is that OpenAI hand that was like rotating that cube. That thing had like motion capture, it had like 1,000 different sensors that had perfect information about everything, and it still failed like 75% of the time or something, right? Like, you know, so I think what's going to happen is as these systems start moving out of the lab and into, you know, production, quote unquote, these kinds of issues are going to become much more prevalent, right? Because you can't over-engineer the real world. And there, I think the argument is, listen, I know you have a lot of data. You can get a lot of data if you need it, but data is expensive, right? And so if you make this small change in, let's say, the physics, or you add an extra sensor here, it'll save you, you know, X amount of dollars in compute cost or engineering time, right? That would be the pitch. Now, do I have a killer application where I can make that case convincingly? Not yet, but maybe we can talk and find one. Yeah.
Thank you. I think that it's a good time for people, if they need to move to their next meeting, to stop here, and Nick will be around for a couple of more minutes if you want to continue the discussion. So thanks again.
I like to call out. Your representative, your side.
Yeah.
No, it's just too many things the same. That's why somewhere in one of those papers they could
Yeah, I mean, so I think what you're just getting here is there's a notion of symmetry and yeah, I mean, so that's something that I love to think about a little bit. I know there are folks that have like, you know, invariant, equivariant, RL, learning, all those kinds of things. That's really what they think about, right? So there's two kinds. Like one is you use the symmetry to do data. Right, you have to take one piece of data.
Yeah. Person's grand stuff, right? Yeah.
We have a very, you know, also said